Okay. Yeah. Proceed.
Okay, like in question 2.
Okay.
Okay, so for the volume flow rate, he just took the.
What did you answer for the first question?
My answer for the first question was velocity distribution.
Correct. Correct.
Okay, then a second now. Can I just send you my solution for number 2? I think
okay. No issues. Send me. No problem.
I think there's no problem for 2. I still understood it. It's not that bad. The others were really bad. So this is.
Yeah. Got the question. It is a given data where water enters 2 centimeter diameter, right? I think I have issues with your sound.
Yeah.
Wait. Was connected to a wrong router. Okay. Am I audible now? Hello? Am I audible?
Hello?
Am I audible now?
Yeah, better now. Yes.
Okay.
I didn't hear anything.
Okay, no issues. I will just share the screen again, the one I have sent just now.
Yeah.
Okay, this is the question. The water enters 2 centimeter diameter, 3 meter long tube.
Yeah.
Whose wall are maintained at 100 degrees Celsius. Water enters this tube with a bulk temperature of 25 degrees Celsius and volume flow rate of 3 meter cube per hour. Reynolds number for this internal flow is. Okay. Okay, it doesn't look like there's anything difficult in it. Okay.
Yeah, it's not bad. I just didn't get the volume flow rate portion of it. Why we had to.
Okay, see, volume flow rate, basically, if you remember, we had discussed the mass flow rate formula. The mass flow rate is basically density into volume flow rate.
Yeah.
Right?
Yeah.
Many times what happens, they instead of giving you the velocity, they prefer giving you the mass flow rate. So using the volume flow rate, you can find the velocity.
Okay.
Okay. What is volume flow rate? Volume flow rate is area of cross section into velocity. Okay.
Yeah.
Just for simplicity, what you should do, you should remember or write it down this formula, like m dot is called as mass flow rate. It is equal to density into volume flow rate. It can also be written as density into area of cross section into velocity. You should remember this formula throughout. You will need this like in many places.
Okay.
Okay. So now here you have got volume flow rate. Volume flow rate, when directly multiplied to density, will give you mass flow rate.
Yeah.
Okay. The tricky part was they have given you volume flow rate per hour. You should multiply it by, divided by 3600 to convert to volume meter cube per second.
Yeah.
Okay. So to find the Reynolds number, the formula is rho Vd by mu. Right? Re is equal to rho Vd by mu. V is velocity. Look, the question has already given us mu, whereas density, they have also given you 2 centimeter diameter.
Yeah.
So you've got density, you've got viscosity, you've got diameter. All you need is velocity, right?
Yeah.
Okay. The velocity can be easily calculated by using the mass flow rate formula or volume flow rate formula. Volume flow rate will be area of cross section into velocity. So this can be equated as volume flow rate is equal to area of cross section into velocity.
Yeah.
Area of cross section of pipe is pi by 4 d square or pi r square, whatever you take, pi by 4 d square into velocity. Right?
Yeah.
Volume flow rate is given 3 meter cube per hour. So it will be 3 meter cube per hour. You will divide it by 3600. It will become meter cube per second.
Yeah.
Now this is in meter cube per second. Area of cross section will be pi by 4 and diameter is 0.02 meter. Right?
Yeah.
and velocity is unknown. From here, you can find the velocity.
Velocity. Okay.
Once you have velocity, I think this is the velocity. They have done the exact process. I mean,
Yeah. I was just wondering why we had to do it because I didn't understand fully.
Okay. I hope you understood now.
Yeah, I do.
Okay.
And then we just input into the formula of
Yeah.
Reynolds number and I get the answer, right?
Yeah. For such cases, always remember m dot is equal to rho a v, where a is area of cross section, whereas v is velocity.
Okay.
And together, area and velocity is called as volume flow rate.
Yeah.
Okay. Like many times they might give you mass flow rate. Using that mass flow rate also, you'll have to find the velocity.
Okay.
Yeah. So let's proceed. Any else stuff?
Yeah. So number 3 also I tried.
Okay.
Not too bad. I understood it, but I just want to like be clear about something like the isothermal.
Okay. Number 3. The number 3 is area CP. Air CP is given. Enters 17 centimeter diameter and 4 meter long tube. Right. This question, right?
Yeah, correct.
So it enters a tube having 17 centimeter diameter. It has length of 4 meter. Okay. And I think it is inlet temperature 65 degrees at the rate of, this is mass flow rate. Okay. So now this is m dot.
Oh, how do you know? How can you tell if that's mass flow rate or otherwise volume flow rate or the units?
Unit.
Okay.
Mass has the unit of kg, volume has the unit of meter cube. When they are divided by time, it becomes rate.
I see. Okay.
Okay. So now this is m dot. Whereas this was volume flow rate, v dot.
Yeah.
Okay. I think now it might be sorted. So they have given you mass flow rate. They have given you inlet temperature and outlet temperature.
Yeah.
The tube is observed to be nearly isothermal. It means it remains constant throughout. The temperature of the tube remains 5 degrees Celsius throughout.
So that's when you use the log mean temperature difference.
Yeah, true. The T surface is maintained as 5 degrees Celsius. T inlet is maintained as entry, right? You use entry. Inlet is maintained as 65 degrees Celsius.
Correct.
And the end or the outlet is maintained is 15 degrees Celsius. So you can find the log mean temperature difference easily. It will be delta T1. I hope you remember the procedure where we draw a graph.
Yeah, I sent you my solution. Oh, yeah. Okay. Another thing, I need to know how to draw this graph thing to understand better.
Okay. I will give you one generalized method wherein which you can use or you can apply everywhere. So the graph is basically temperature of two fluids. So, for example, in this case, they have given us the tube is maintained at 5 degrees Celsius. So that temperature is not changing because they have mentioned it is isothermal.
Yeah.
And 5 degrees Celsius is much lesser than 65 and 15.
Correct.
Okay. This graph is basically length versus temperature.
Okay.
Length means if you imagine a tube will have a length, right?
Yeah.
So it's like a tube in which fluid is flowing. It will have, I will draw tube below the graph. So it will be very easy to imagine. Let us say there is a tube. This tube has maintained the temperature of 5 degrees Celsius. T surface is equal to 5 degrees Celsius at the outlet throughout the surface.
Okay.
Then one of the fluid is entering inside, which is hot fluid. A hot fluid is entering inside and colder fluid is leaving inside because tube is at lower temperature.
Yeah.
Okay. So this was entering at Ti is equal to 65 degrees Celsius. And this is equal to T end or T outlet is equal to 15 degrees Celsius. The temperature got decreased because of the outer temperature 5 degrees Celsius.
Yeah.
So you can clearly see that one of the fluid is having decrease in its temperature. So if this is a graph, that graph will have a representation for the fluid in such way. Like at entry, it is 65, right?
And then end is 15.
15. So you can clearly see the graph is declining.
Yeah.
Slope is lowering. Whereas the other fluid will have a constant horizontal line.
At 5 degrees.
True. Right? So this will be the graph in this case.
So how does this graph help me to solve the question?
Okay, this graph will be basically helpful to find the delta T1 and delta T2.
The change in temperature?
Like delta T1 would be inlet temperature difference. Delta T2 would be outlet temperature difference. Over here it will be 5 degrees Celsius. Over here it will be 5 degrees Celsius. Delta T1 can be taken as 65 minus 5. 65 minus 5 equal to 60 degrees Celsius. Delta T2 can be taken as 15 minus 5 equal to 10 degrees Celsius.
Okay.
Delta T mean will be equal to delta T1 minus delta T2 upon log to the base E delta T1 by delta T2. This will be equal to 60 minus 10 upon log to the base E 60 by 10. And this will be a mean temperature difference.
Okay.
Okay.
Yeah.
Did you find the value?
I sent you the solution for number 3.
Solution.
That I did.
Okay. Is this one? Yeah. Yeah. See, even we have drawn the same graph.
Yeah, because this one I followed the lecturer. So I just wanted to understand it better. Like, why are we drawing this? And
the graph is basically just to understand the temperature difference. See, even for me, this complicates, the representation actually complicates. Like taking 4 to 3 temperatures in the graph, and if you forget with the sequence or make a mistake in the sequence, you might end up with a wrong value.
Okay.
Isn't it? Like it is difficult to by heart or mug up this. So instead, the method would be simply
to draw it out.
Okay, I will share the whiteboard again. Okay. Okay. See, like in your solution, they have also written the temperatures, but remembering those values are very difficult. Instead, this is easier to understand. Delta T1 is something at entry, delta T2 is something at exit. What is delta T? Temperature difference. Temperature difference. Okay. Now, sometimes you might take 65 minus pi.
So that means for this solution that I sent you, is my log mean wrong? Temperature mean wrong?
Use the calculator and tell me the value, what I have written, like 50 upon log to the base 60 by 10, how much is it?
Yeah, see, that's why I wrote different values for mine. That's why I was wondering this wrong.
Okay, I will just check mine.
Yeah.
Is 50 upon, and then 50 by 60 by.
This one I got 27.905. This one also I got 27. How's that possible? Let me just check. Yeah, I got the same answer for both. Like yours is also 27, mine is also, but my solution is wrong, I think.
Okay, we'll see the solution. What is wrong with the solution? No problem. Okay, I hope you understood how to find the delta T, right? Log mean temperature difference.
Yeah, I do. I understand that. No problem.
Okay, see, it is very it will get very difficult for you if you simply go through the solution. You should understand how to write it down yourself. Every question will have a different situation. Like in this case, the graph is in such way. In some question, the graph might change. Like you might have a horizontal graph upward and a fluid going like this. So even in that case, just take delta T1 over here and delta T2 over here. You will never go wrong. Like if you take delta T1 on the left, delta T2 on the right, delta T is basically temperature difference. Just simply subtract the bigger temperature with smaller, bigger temperature with smaller, or the one over here minus one over here is delta T1, the one over here minus the one over here is delta T2.
Yeah, I understand that.
Okay.
So I can confirm that this is wrong, right? What I did, the one you circle in pink is wrong, right?
No, wait. I'll not conclude. Let me see. I haven't gone through it. Okay, clear.
Because they were not clear with the formula when I looked through the lecture. Even he got confused, the lecturer, so I got confused even more.
Okay. So does this value match with ours?
Yeah, it's the same value.
Okay. What have they calculated? The question is asking about okay. Leave that the tube is observed to be unilateral. The average convection heat transfer coefficient. So H is asked. Constant temperature, log mean temperature difference. Okay. mCp dt. M dot into Cp into temperature difference. Correct. Okay. So you got this Q, and then that Q was divided by surface area. Surface area is circumference into length.
Mm-hmm.
Where okay, yeah. This is the surface area, circumference into length.
Yeah.
I think procedure looks right to me.
So why is the one you circled and the one that you did is completely different?
No, it is same. It is one and the same.
The values are different. Only the final answer is right.
Values are different. No, they are same. Values are same. It is all about mass. See, I'll explain. Don't worry. Okay, understand.
Like I think.
Okay, understand the property of log. Am I audible?
Yeah, I can hear you.
So just understand how log works. Over here, this formula,
Mm-hmm.
they have simply taken difference between this temperature and this temperature.
Yeah.
Because it is mathematically adjusted. It is like what I am using is the main formula, and that formula is simplified and written in this way.
Oh, okay.
Like what I am using is the general formula, main formula.
Okay.
With that formula, you can solve any question.
Okay.
But using this formula, you cannot solve all the questions.
So if let's say I use your formula, will I get it wrong?
You will never go wrong.
But will they mark me wrong?
No, never.
Oh, okay then. Okay. So I should just stick to your formula then, since I can use it for all.
Yes. Just make sure that you are mentioning what is delta T1 and what is delta T2 over here before substituting. Okay.
What do you mean by mention?
Mentioning, right? You'll have to write down what exactly is delta T1. Don't simply substitute them without telling them what exactly it is. Like delta T1 would be 65 minus 5. Just write it down before you substitute.
Okay, I get it. Okay.
Because they'll be like, you have skip the step and they might cut your mark.
I see. Okay, I get it.
But I think everything looks easy to me and same. Nothing difficult over here. But I hope you understand the procedure. Do you understand what exactly they have done?
Yeah, I understand.
Okay. Now can you explain to me what exactly they have done?
What exactly? What? Sorry, didn't hear you.
Explain to me the procedure. What would you do if the question appears in the exam?
Oh, this question.
Yeah. Steps. What would be the step you would follow?
Okay, so I'll use that formula, the first one, to find out the energy.
What formula is that? Do you know the formula? Can you use it yourself, or you'll have to by heart it? Like you'll have to know that in this question you have to use the formula. Do you know that?
No, I'm not. I can't recall.
Okay, so this is. I just wanted to know this because it is not about just remembering or mugging up this question. You should be ready to tackle with any question. So, what should be the mindset? Formula of heat transfer, Q.
Yeah.
Okay. What are all the formulas you might have to use in this case? The first formula is HA delta T.
Yeah.
Right? What is HA delta T? It is heat transfer formula.
Yeah.
It is formula of heat transfer. It is the heat flow rate or heat transfer per unit time, right?
Yeah.
Okay. Logically, you should understand that if there is a tube in which fluid is flowing,
Yeah.
either it will get heated or it will be getting cooled.
Yeah.
And it can be. I'll just take this call, okay?
Yeah, no worries.
Hello. Yes. हाँ डियर बोलो ना मैं अभी भी लेक्चर में लेकिन बोलो ना चलेगा डियर कोई बात नहीं हाँ, मैं आपको एक ग्रुप का लिंक भेजा शायद आपको मैंने ग्रुप का लिंक भेजा था टीई का अच्छा फीस के रिलेटेड ग्रुप पे डिटेल आ जाएगा डियर अभी तक भेजा नहीं किसको भी आ जाएगा उसमें हाँ ओके ओके See, this is the heat transfer rate, heat flow rate. It means it is the heat absorbed by the fluid per unit time.
Okay.
And then another formula is Q is equal to mCp dt. Now, what is this formula? This formula is called as formula of heat storage or heat capacity or heat gained or heat lost. You understand? So this formula comes from the definition of specific heat.
Sorry, can you repeat this one again?
Okay, this is equal, Q is equal to mCp dt is basically heat either lost by the object or gained by the object.
Heat lost or gained by the object. Okay.
Talks about particular fluid or particular object. Whereas this formula talks about two systems exchanging heat.
Okay.
It's like if there is one body and there is another body and one is radiating, another is absorbing, then how much heat is being absorbed by this body or how much heat is being emitted by this body is basically relativity. It talks about how much relatively heat is getting transferred per unit. Right? Okay.
Yeah.
Then if you simply asked that initially it had some temperature and after losing out heat, it will have some different temperature. Maybe temperature reduces. So if I'm only concerned about this body, if it has lost some heat, then only for this body, you will have to use formula equal to mCp dt.
Because it's for a particular object.
In this case, dt is basically temperature difference of the same body.
Okay.
In this case, the temperature difference is between the two bodies.
Okay.
Right?
Yeah.
So mCp dt has got temperature difference of the same body with time. Like it is function of time. At the beginning of time, it will have some temperature. At the end of time, it will have some temperature. And that temperature difference is dt.
Okay.
So in this question, they told us that a water or a fluid, I think it is air, right? Air entering the pipe and initially it has 65 degrees Celsius temperature. Then it got cooled and later on it has temperature of 15 degrees Celsius.
Yeah.
So what happened?
Heat was lost.
That air lost the heat and the heat lost can be taken as mCp dt of air.
Okay.
Right?
Yeah.
For simplification, you should remember if you have temperature of the same body, like initial temperature and final temperature of the same body, you can easily use mCp dt anywhere in any question.
Okay.
If you have initial temperature and final temperature of same body, you can use this formula.
Okay.
If you have temperature difference between two bodies,
then I use the first one.
Yes.
Okay.
Okay. So in this case, they gave us an air entering a tube initially at 65 and leaving at 15. So we got to know that, okay, some heat has been lost and after losing heat, the temperature of air reduces. So what we calculated initially or in the first step was how much amount of heat did the air lose.
Okay.
So since air lost this much amount of heat, we can relate it with the property that if one body is losing, another body is gaining, right? Then
Yeah.
net heat exchange, net heat transfer will be equal to the heat gained or heat lost.
Okay.
See, understand? One body is emitting, another body is receiving.
Giving you.
Net exchange.
Mhm.
That net exchange is basically heat transfer.
Yeah.
It can be equated with the heat lost by the body, and lost by the body formula is mCp/dt.
Okay.
That's why you can equate both the Qs, HA delta T and mCp/dt.
So when I use the first formula for this question, which is the HAS delta T,
Yes.
that is for between the fluid and the
Pipe.
pipe, right? Because
Right.
there's two bodies.
Right.
Okay, got it.
And see, and both the values can be equated. It means Q transfer. It means Q transfer is equal to Q lost. So we can say HA delta T is equal to mCp/dt.
Yeah.
And you have done that exactly in this question. mCp/dt was calculated and then this was equated over here.
Yeah.
Right? Delta T over here is delta T mean. Delta T over here is delta T mean. Okay. One complicated situation would be, what if delta T1 and delta T2 is same? What would you do?
No idea.
When delta T1 will be equal to delta T2, log of same value is 0.
Yeah.
Log of 10 by 10, log of 1 by 1 is 0.
Mhm.
And anything upon 0 is not defined.
So there's no heat. There's no.
No. In that case, you have to take delta T mean is equal to delta T1 equal to delta T2. In that case, don't use delta T mean formula, okay?
Okay.
If the temperature difference at entry and temperature difference at exit is same, directly take them equal to delta T mean.
Oh, okay.
Okay, that can be one of the situation you might face.
Okay.
Okay. Okay, this question looks easy.
Yeah.
I think we should proceed.
Okay.
Let's take another question, okay?
Yeah. So the next one I have is question 4. This is where it's really stuck.
Okay.
Okay, I'm just gonna.
Have you sent me?
Yeah, send it.
Okay.
Actually, this one, can you do it and then I go through
Yeah,
it?
no issues. Which question?
I don't think I have the full thing here. I'll just send you what I have first, but I would like to see how you do it, if there's a different way that makes sense.
Okay. Are you talking about that 50 centimeter to 50 centimeter circuit?
Oh, no.
Okay.
Question 4. The 5 mm diameter first.
Okay. We will solve it here only. Like the way question is given, I will just share it with you on the WhatsApp and we will solve it over here only. Let's try to solve if it is possible. Can you see the screen?
Yeah. I'll just send you what I have first.
Yeah, no issue. Send me.
No, I only got that far. After that, I just didn't understand.
Don't worry. Look, I would just suggest, never try to understand the procedure of question and try to copy it as it is, because you might end up with a wrong sequence in exam. But if your concept is clear, key what exactly need to be done, what should be the required step in this case, if you understand everything practically, it will get very easy.
Okay.
So don't try to just mug up the procedure what your teacher has given. Okay, we will
Okay.
try to solve it the way like as if even I don't know what the question is, and if this comes in exam, what should be the required step. Okay.
Okay. Okay.
Yeah, I think I have received.
Yeah. Can I take a second? I just want to get some water.
Yeah.
I'll be back. Hi.
Right.
Yeah.
Okay. Okay. The water enters a 5 mm diameter and 13-meter long tube.
Yeah.
At 45 degrees Celsius with velocity 0.3. Tube is maintained at constant temperature. The required length of the tube in order to water to exit the tube at 25. Okay, they have asked us required length. What should be the length of tube? It is very easy question.
Is it?
Yeah, very easy. Don't worry.
I don't know. I was so lost.
Why have you calculated the entry length, by the way?
I don't know. He calculated the entry length. So, because I remember them saying in the lecture that if it's either like laminar or turbulent, right?
Okay.
And then he took it as developing or something. And then I got lost.
Okay. We'll just read the line, okay, which are written. See, entry length, L thermal has been calculated. And what you have written is since the length of pipe is 13 meter. Okay, length of pipe is 13 meter and thermal boundary layer is less than that, then the flow is still developing. How come?
I don't know. I don't know.
Very simple. If the entry length is 2.5 meter, it means boundary layer has been formed.
Okay.
Like, see, if this is a tube and it enters after 2.5 meter, the boundary layer or the profile has been formed.
At 2.5, is it?
Yeah, right?
Yeah.
2.5. Right? 2.5 meter. And the length is 13 meter. So it has been formed. It has been already developed. That line makes no sense to me actually.
Maybe I heard it wrongly, but what about the steps after that? Does it make sense?
Okay. We'll see. I haven't gone through it. Okay, work with this amount.
Yeah. You can just ignore whatever.
Okay.
Probably only I understand it here and there.
Okay. L laminar is 0.5 meter.
Can I maybe share with you how he went through this? Then you can.
Okay. Send.
Yeah. Okay. Can you allow me to? I think, can I share? You have to let me share.
You can share.
Yeah.
Multiple share. Yeah. Now you can do it.
Okay. Let me just. So what's that something here? I think this is the one. Yeah, I think this is the one.
Okay.
So take the whole thing. I'll have to just right now. If we go back and see with the constant surface temperature, we need to use our log mean temperature difference. So in this, let's draw this out. So if you
This is
get
for
one of
the
these
previous one.
questions, in the
Get to the question.
exam,
Yeah, I just
and you're not sure.
No, this is
This one is the question number 3, right?
yeah.
Get to the question number.
Gonna
Yeah,
run out
this
of
one.
time.
So,
But see how we went.
yeah, I think this is it.
Characterize the flow. So find out what the Reynolds number is. We can do that straight away. I think all the values were given then. So that is 994. Velocity 3.
It's not very pleasant to the ear.
Yeah. They're not very clear.
Mu was 72 times 10 to the negative 3. I did this as well. And that was 2070 about.
So this was the one he didn't give us the 0.72, how he got it. And then I asked you.
Yeah. I hope you
Yeah.
understood.
Yeah.
You must be reading some solution, I guess.
Not that much.
You must be having some solution
Yeah, I have a
If
feeling
you didn't get
because
similar value, just let me know and I can put in what you got, see how it went. Now we need to find out what the length of the pipe is. We have two assumptions. We can assume that the pipe is fully developed or is currently in the developing stage, and we don't know, so we will need to calculate for both. So what is the fully developed region? Length. Fully developed length is given by 0.45 Reynolds number times the Prandtl number times the diameter. Go back up, it's this equation here. Thermal, well, we don't have it in these slides, but you should have it for your thermal boundary layers. Hydro. So the difference between thermo and hydro is that we have the Prandtl number involved for thermal. For hydro, we have 0.05 Reynolds number, the diameter. So both of them need to be fully developed. Or we need to see which one is the shorter one. And because our Prandtl number is 0.7, we're going to work with the thermal boundary layer. That's when it starts to become fully developed. So here we have 0.05 divided by 2070, and the Prandtl number is 0.7. 4.83, sorry. And diameter is so we've got this length. I did calculate that. That was 2.5 meters. So the thermal boundary layer takes 2.5 meters to develop, and the hydrodynamic would take so it's going to be shorter, isn't it? So we need to find out, I mean, both of the boundary layers need to be fully developed to be assuming that the entire flow field doesn't change anymore. So we're actually going to work with this because although the velocity boundary layer is fully developed earlier, the thermal boundary layer needs to continue to develop. So if we are with the flow field, if the length of the pipe is less than 2.5 meters, then the flow is still developing. Did we have developing equations here? No. Did you get the developing equations in your slides? I think you will have them in your other slides from Dr. Raj. I will go through it with you now. So first assumption is developing flow. If we assume it's a developing flow, then Nusselt number is quite lengthy. It's 3.66, 3.65. D on L. That's Reynolds number times Prandtl number. By 1.04. D on L. That's Reynolds number times Prandtl number. Power of 2/3. And the other assumption is but we don't need to do that yet. We find that in our pipe, starts off fully developed, and the question is saying how long, find the required length of the tube so that the temperature exiting here is 25 degrees. If we find that this length is similar to 2.5, it may be even a little bit more, right? Then let's say, I don't know, let's say this was 3, and here we're at 2.5. We know that there's a larger proportion of the pipe that's fully developed. Then it's okay to assume that the flow is developing. if it's about halfway, then it's a bit harder. We may have to calculate both developing and fully developed. Take
You can pause it.
each. If it's only a tiny bit,
Sorry.
Let's pause and I'll do it ourselves. Okay.
Okay. Yeah.
Okay. What did you understand? Just let me know.
Ah, nothing.
Okay, I'll tell you what he's trying to explain.
Can I stop the share?
Yeah. Issue. No issue.
Okay.
Okay. See, the question is like water enters 5 mm diameter and 13 meter long tube at 45 degrees Celsius.
Mhm.
So there's a tube in which water is entering at 5 degrees, sorry,
45.
45 degrees Celsius.
Mhm.
With velocity 0.3 meter per second.
Mhm.
We've got diameter, which is 5 mm, 0.005 meter. And the total length is 13 meter.
Yeah.
L total is equal to 13 meter.
Mhm.
Tube is maintained at constant temperature of 5 degrees Celsius. T surface is 5 degrees Celsius.
Mhm.
The required length of the tube. Okay. Now the question is, what should be the length of the tube, or maybe at what length of the tube the temperature of water would be 5 degrees Celsius? The question is like, it is getting decreased. Maybe let us say at the exit over here it is 10 degrees Celsius or 7 degrees Celsius. That is not the concern. That is not something which they are asking. What they are like is, at what distance of this tube will the temperature of water be 25 degrees Celsius?
Yeah.
25 degree Celsius. Okay.
So we do not know the exit temperature, is it?
No, we don't need this temperature. We are not supposed to know this temperature for
Okay.
30 meter. We
Okay.
need to find that particular length at which the temperature would be 25.
Okay.
That is the question.
Mhm.
That is the required data, or that is something that they want. We have got K, conductivity value 0.623. We've got kinematic viscosity 0.724 into 10 raised to minus 6. We've got specific heat 4178. We've got density 994. We've got Prandtl number 4.83. Okay. Now what should be done? See, in this case,
The fluid is losing heat, so you use the Q equals to mass flow rate Cp delta T.
we can use formula mCp dt.
Okay.
We have got cross section, so mass can be written as m dot. M dot is rho av. It will be rho av into Cp dt. This is the formula of Q lost by the water. Rho would be 994. Area of cross section will be pi by 4 d square, 0.005 square. Right? Velocity is also given, which is 0.3. This is rho av, okay? Rho av. Cp is also given, or we should always know what is Cp. 4178.
Mhm.
Okay. Then next is dt. dt is 45 minus 25.
Yeah.
So with this, we will have total heat lost by the water.
Mhm.
Now this can be equated to HA delta T mean.
Mean. Yeah.
A would be surface area,
Mhm.
right? And H, if the entire question is about H, by the way, H.
Yeah.
They haven't given us H. Had they given us H, things would have been so easy.
Mhm.
All we had to do is AS is something we need to calculate. Because delta T mean would be delta T2 minus delta T1 upon ln delta T2 by delta T1. What would be delta T2? Delta T2 would be 45 minus 5, 40. Delta T1 would be 25 minus 5, 20.
Over 1.
40 by 20.
Yeah.
Whatever you write first, just take it in the numerator. Whatever you write second, just take it in the denominator.
Okay.
Okay. So delta T mean is calculated. H, if we have H, surface area formula would be pi dl. Pi dl, and this is something which is required. Pi and diameter is 0.005 into L.
So L we do not know.
We need to find that L. That is the entire question all about.
Okay.
Okay. So just to find L, which is part of AS. So AS is unknown. Delta T mean is known. We can easily calculate MCP dt. Right? Let me calculate MCP dt. MCP dt would be 994 into
Is it
4.
1957?
Okay. I'll just cross check. 0.05 square into 0.3 into 4178 into 20. How much?
1957.
Okay.
Did I get the wrong answer?
You've got the same values, right?
I didn't get the answer. Okay, wait, let me check again.
Have you used the same values which I have used?
No, I used my own.
What, like the density?
No, the area.
What area have you taken?
Pi r square.
Oh yeah, pi r square is fine. What is R? What R have you taken?
Oh, okay.
It's a diameter. It's not.
Yeah, I forgot.
Okay.
Okay, I got it. What was it?
It is 489. Okay.
489.
489.26. Okay. It is in watt.
Okay.
Joule per second. This is something everyone does. Pi r square, then
Yeah.
R over here. It will be 0.0025.
Yeah.
Okay. I'm into habit of using pi by 4 d square.
Oh, okay.
It's okay. So now I have got Q. Q can be taken over here. Right?
Yeah.
This is now 489.26, which can be equated. Just use your calculator and tell me the value.
$28.85.
Just a minute. How much? 20?
8.85.
85.
3.
Okay. $28.854. Okay. 39 can be taken as 4. See, now we have got delta T mean. Now if we substitute over here, this will look like H into pi into 0.005 into L into 28.854. This is the main required answer of this question. So we need to have H to solve it. How to find H? Now convection chapter is all about finding H.
So we find the Nusselt number.
Yes, for that we need a Nusselt number.
Yeah.
Okay. Now whenever a length part is asked, things get tricky. Like if the question is like if it is given for fully developed flow, you will always go right. But
Okay.
sometimes these questions play with you. They're like, let us trick and ask the length and have a length within the developing range. But
Okay.
having the length within the developing range complicates the question.
Okay.
So what your teacher did, he actually assumed developing flow.
Okay.
I would always go for developed flow. Let us say the flow is developed.
Uh-huh.
Then that is safe when the question is actually not tricking you.
Okay.
But if question is tricky, you might even end up wrong and you'll have to go for developing flow. So it all depends, examiner to examiner, what kind of question is setting. So
Okay.
let us initially assume developed flow.
Okay.
Okay. With this, I will make a conclusion. Okay.
Assume either one of them I won't go wrong, or depends on the lecturer.
No issue. Just go with this. You can go with developed flow assumption. Assume developed flow because both are assumptions.
Okay. So I have to write this down before I find my Nusselt number.
Yeah. Because you'll have to find two Nusselt numbers.
Okay.
Okay. Initially, let us assume developed flow.
Mm-hmm.
And for that developed flow, find the Nusselt number.
Mm-hmm.
Find the value of H. Then find the value of L.
Okay.
And that L, we need to compare with developed flow L.
Okay.
You're getting me? Like if you remember the value of L was
13.
L thermal was
Just now. 0.5.
RE, PR.
Yeah, D, I think.
Yeah, correct.
Yeah.
So 0.05. This will be rho V D by mu. Then PR is something which is 4.83.
Mm-hmm.
4.83 and diameter is 0.005.
Yeah.
Let me substitute 0.05 into density 994, velocity 0.3, diameter 0.005, dynamic viscosity. They've given kinematic viscosity. Okay. So in that case,
Dynamic is 0.72 times 10 to the power -3.
yeah, what I will do, whenever they give us kinematic viscosity, you can avoid the density. Take it VD by nu.
Okay.
Okay, if you can get rid of one of the step. So it is like 0.3 into diameter 0.005 and kinematic viscosity is 0.724 10 raised to minus 6. 0.724 into 10 raised to minus 6 into 4.83 into 0.005. Okay. What was the value?
I got 2.5 meter.
2 point?
I'll check yours though. 0.05 times.
Two 2.5. I've got
2.5.
2.5017. Okay.
Yeah.
This is Reynolds number. Okay. Reynolds number, if at all it is required, we can calculate and keep it separately. Because Reynolds number is something that will signify if we need to use the equation of laminar flow or turbulent flow.
Yeah. Can I just ask you, what is the difference between the L thermal and L hydro something?
L thermal should be always more than L hydro.
What is L thermal?
L thermal is thermal boundary layer, like temperature distribution formation. And L hydro is velocity distribution.
The fluid itself.
Yes, fluid itself. Like if you remember, we had discussion about parabolic profile.
Mm-hmm. Yeah.
Velocity is same everywhere, but after some distance, the velocity forms a parabolic profile.
Yes.
It is very important that this velocity profile is formed way much before than the thermal profile.
Okay.
right? Otherwise, thermal profile will never settle down.
Okay.
Thermal exchange takes place when velocity distribution, like the particle which are moving in a uniform manner. Because if the particle is changing its velocity, the thermal profile will be not stable.
Yeah.
So it is very important that hydrodynamic length should be less than thermal length.
Okay.
It will mostly less than thermal length. Okay.
Okay.
Okay. So if there is a case wherein the length is not less than, if it is more than, then in that case we'll have to take the bigger value.
Okay.
Like developing will be always the bigger value. Like in this case 2.5 I have got for the thermal. The hydrodynamic will be lesser than this.
Okay.
Like hydro value is basically 0.05, sorry, it is 0.05 RE into D, right?
Yeah.
So it is L thermal divided by Prandtl. Right? Isn't it?
Yeah.
So if we divide it by 4.83, the value comes 0.5 something.
Yeah. 0.517 or 518.
So what you should do is, you should always consider the max value out of these two.
Okay.
Okay. The max value will tell you if the flow is fully developed or not.
Okay.
Okay. So now I've got the limitation, or I have got the limiting value.
Mm-hmm.
If the obtained length is less than 2.5,
Mm-hmm.
your assumption of fully developed flow will be wrong.
Okay.
Right? Getting me?
Yeah, I get it.
Because you have assumed fully developed flow, but the flow will actually develop when the distribution is done.
Yeah.
And when distribution is done, it will be done at the length of 2.5 meter. But if the 25 degrees Celsius comes at the length equal to 2 meter,
Mm-hmm.
then the obtained H or obtained Nusselt number was actually for developed flow, which should be beyond this point.
Yeah.
This contradicts your assumption.
Yeah.
So what should be done? The step should be, whenever there is a question of finding the length, you should assume either assume fully developed or assume developing first.
Or
Find
do
the Nusselt number, find the H and find the L.
Uh-huh. And then compare.
And then compare it with this value.
Mm-hmm.
If this value comes, like if you have assumed developed flow, and if this value comes at 2.6, 2.7, 2.8 or 3, then your assumption is right, you can proceed and that is the final answer.
Mm-hmm.
But if you assume it to be developing flow,
Mm-hmm.
and the length comes as 3 meter, then your assumption is wrong.
Okay.
Because for developing, L should never be more than 2.5.
Yeah. So then I start again. So if I do both, I just cancel one away.
Yes. Automatically, you can conclude with one of the answer. Like, let us start the procedure and try to solve it.
Okay.
Suppose we calculated L thermal, and now we will assume, let us assume fully developed. Let us assume fully developed flow.
Mm-hmm.
For that case, what was the relation of Nusselt number for laminar flow?
Checking.
Okay. You had sent me the list, like the list of formula.
Yeah, I'm looking through that too. Yeah.
Let's go through that. Okay. In that case, Nusselt number equation for laminar. Okay.
Mm-hmm.
Where is the equation? Okay, see, if the flow is fully developed, the table is given for the pipe and the surface temperature is constant, the Nusselt can be taken as 3.66.
Where is that?
Just look at this table.
Oh, the fully developed cylinder.
Okay.
This one?
Internal force convection table.
Oh, okay, yeah, okay, got it.
The first column is for fully developed laminar flow.
Okay.
We got RE less than 2300, right? RE was 2070.
Yeah.
So less than 2300. Hence the flow is laminar, correct?
Yeah.
Just if you haven't calculated, just use a calci and check the value if it is less than 230 or not. I think it is laminar flow. 0.
Where did you see the part where it says less than 2300?
That's the limiting value for laminar flow. We have discussed already.
Oh, yeah. I thought it was in the formula.
If more than 4000, it is taken as turbulent.
Turbulent.
If less than 2300, taken as laminar.
Okay.
Okay.
Yeah, it's 2070.
2070.
Yeah.
So we will take it as laminar flow, and in that case, the Nusselt number for pipe, right?
Yeah.
This is T constant, T surface constant. That's why we are taking 3.66. Had it been Q constant, we would have taken 4.36.
What do they mean by Q constant?
Constant heat flux. If question says the constant heat flux is maintained,
Okay.
in this case, they have said the surface temperature is maintained at 5 degrees Celsius.
That I understand. But when they say constant heat flux means?
Constant heat flux means at every instant, the same amount of heat is entering the tube.
Okay.
That is only possible in counterflow arrangement. If you remember, we have discussed counterflow, wherein two fluids are flowing from opposite direction and delta T always
Yes.
constant.
Yeah, I understand. Okay.
So that is one of the case. They haven't mentioned, and also clearly delta T at entry and delta T at exit is not same.
Okay.
That is only true when delta T at entry and delta T at exit same.
Okay.
Okay. So now here the flow is laminar. At the same time, surface is temperature is constant. So Nusselt number is 3.66. Okay.
Okay.
This will be equated by HD by K. Nusselt number is 3.66. Diameter is 0.005.
0.005. K is given 0.623.
0.623. Tell me what is H? H comes 3.66 into 0.623 divided by 0.005.
456.036.
So it is 456.036.
Yeah.
Now what we will do is we will use this equation and we will substitute the value of H, 456.036, and we will find the value of L. Let's do it together. 489.26 divided by pi into 0.005 into 456.036 into 28.854. Things have gone wrong. Obtained L comes 2.367.
So it is developing.
Yeah, so it is less than 2.5 meter. Assumption is wrong. I had this feeling that's why your teacher started with the developing region.
Oh,
That these questions are asked just to trick students.
I see. So if let's say my assumption is wrong, can I just make a note that assumption is wrong? Therefore, the flow is developing. Can I just write that? I have to do all over again.
You'll have to do that. You need to find L.
Oh, yeah.
The answer doesn't end there. Once you do the assumption, you'll have to find the value of L. Assumption is wrong. So the flow is developing. Flow is developing. So now for the developing flow, we will have to do all this again.
Mhm.
In that case, Nusselt number equation. Nusselt number equation for developing.
They don't have it here, right? They are fully developed only.
Okay. Formula sheet doesn't have the formula.
Let me see if I have it in my photo somewhere.
No, can't see the formula. They should give us the formula in exam
Yeah.
because the formula is not easy to remember.
Oh, I think I have it here. I took a picture of it when I was going through the notes.
Okay. Yeah. These formulas are actually not used, because question is very tricky. They are not, these questions are not asked normally in exams. These are good to
Oh.
discuss the topic and understand the concept, but
Mhm.
not in exams. Like the question becomes very lengthy.
Yeah.
And they themselves have not given the formula in the formula sheet.
Yeah.
Maybe because they are not expecting it to be asked.
Oh, could be.
That is a good question. REPR raised to 2 by 3. Okay. D by L is the ratio of diameter to length, right?
Yeah.
Yeah. Diameter to length. So let us substitute. We have everything. 3.66 plus 0.065 into 0.00. How many zeros?
Um,
2 zeros.
Yeah.
5 by 13 into 2070.
Yeah.
2070. Prandtl was 4.83
Mm-hmm.
upon 1 plus 0.04, 0.05,
005.
005 by 13 into 2070 into 4.83 raised to 2 by 3.
The raised to 2 by 3 is for the whole thing from the diameter over length all the way to Prandtl. Yeah.
My bad. Okay. So let's use the calculator.
Yeah.
0.065 into 0.005 divided by 13, 2070, 4.83, 1 plus 0.04 into 0.00. Five, 13.
I got 3.88.
3.888.
Yeah.
It is 3.8876. Okay. So this is the number. Nusselt number can be given by H D by K. H will be 3.8876 into K divided by 0.005. K was 0.623.
Mhm.
0.623. Answer into 0.623 divided by 0.005. 484. 484.396 watt per meter square Kelvin. Okay. Now let us substitute in the equation of Q, which was HA delta TLM. H A delta TLM, HAS delta TLM is equal to 4 something, no? 489.26. 489.26. H is 484.396.
Sorry, sir, your H is what value?
483.
How did you get that?
How much did you get?
I
483.
got 498.
You got 498.
Yeah.
What did you take? 3.8876 or 3.888?
Oh, sorry.
No, no, it's okay. Maybe you must have taken 3.888, right?
I did 3.99.
Oh, okay.
I think it's too late then. I'm seeing things. Okay, 484 is right, yeah.
It must be, I think, 1 o'clock over there.
No, it's 12.
It's 12?
Yeah.
2
Getting
and
it wrong.
right.
Yeah.
Yes.
Yeah, it's okay. 484, yeah, I got that.
Diameter 0.005 L. Delta T LM was 28.854.
Mhm.
Okay, let's calculate L. L would be 489.26 divided by pi into 0.005 into 28.854. 2.228, which is less than 2.5 meters. Hence, assumption is correct.
Right. Okay.
Okay. So this was the question, and this is how you can solve it.
Okay. Yeah. Okay.
Did
I
you
get
ask
it.
anything about this?
No, I'm good.
Okay. So shall we proceed with the another question?
Yeah, yeah.
Okay. The next question is question number 5. Air is 10 degrees Celsius. Air at 10 degrees Celsius enters a 18-meter rectangular cross-section duct. Okay. Air at 10 degrees Celsius enters 18-meter long rectangular duct cross-section. Velocity. Duct is subject to uniform radiation hitting throughout the surface. Okay, see, this is the case which has Q constant.
Okay.
Understood?
I'm reading it. Give me a second.
Okay.
Oh, so uniform radiation tells me that it has Q constant.
Even if they would have said uniform heat flux rate. Uniform
Oh, okay.
heat flux. Heat flux is heat flow rate. Radiation is also heat flow rate.
Mhm.
Okay, uniform heat flow rate is something which is Q constant.
Okay.
Okay, so in this case, we will have to use that equation of Nusselt number,
Okay.
Q constant. So, look straightforward, find the wall temperature at the exit of the duct. Okay, wall temperature at the exit of the duct. T wall. Area is given, velocity is given, density can be is also given, m dot can be calculated, Cp dt, m Cp dt. We don't have the exit temperature of air, right? We don't have. Okay, but Q is given.
Yeah.
So Q is given. Q is equal to 400.
Yeah.
Okay, now this can be equated to H delta T Lm also can be written as equated to Cp dt also. Why? You know, because it is in watt per meter square.
Mhm.
Getting me? So it has got the unit of watt per meter square. It means Q by A is given. We know the formula of Q equal to m Cp dt.
Yeah.
N is rho AV. So we can write down rho AV Cp dt.
Yes.
Q by A will be equal to rho V Cp dt.
Okay.
Also, it is equal to HA delta T Lm. So
Okay.
this A is surface area. Okay.
He used this formula. Does that make sense?
Which formula?
This one I'm showing you now.
No, I can't see the camera because you.
Oh, because of my. Okay, I'll just take a picture and send you.
Okay, Q can be multiplied to area, so it will be Q. So we can take 400 into pi dl equal to total Q. Even that can be done. Okay. No, not dl. Sorry, surface area of rectangle it is. So it will be
Yeah, I see.
0.15 plus 0.2.
Yeah, he did that.
And multiplied by length will be equal to Q. mCp dt. Exactly, they have done the same in the first step, right?
Yeah.
So this is equal to 18 meters. Q can be calculated, right?
Mm-hmm.
You understood, right? Why I'm multiplying it by A?
No, not really.
Okay. See, the Q,
That is surface area, is it?
yes.
Because it says the uniform heat radiation. So throughout the whole surface area of the pipe.
What it means, you know, like if there's a duct or a pipe, in
Mhm.
this case, it is heating or cooling the fluid. It is heating, okay. So we
Yeah.
can say that it is transmitting heat to the fluid per unit area. It is
Yeah.
given as 400 watt per meter square.
Mhm.
At every meter square, 400 amount of watt of heat will be getting absorbed in the air.
Yeah.
So what is this? This is equal to small q. Small q is Q by A.
Yeah.
You can look at the unit. It is watt per meter square. Watt per meter square.
Yeah.
Okay, it is called as heat flux if you remember.
Mm-hmm.
Heat flux. I think we had this discussion in the last lecture. Heat
Yeah.
flux is watt per meter square.
Mhm.
So if you multiply the Q by A, you will get Q.
Yes.
Okay, so that is exactly what I have done. To find the Q, I have multiplied this small q with surface area.
Okay.
Okay, so what would be the value? You say calculate.
5040.
It is
5040.
okay, 5040 watt.
Mm-hmm.
So this much amount of heat is getting into the air per second.
Mm-hmm.
Okay, this can be equated to mCp dt.
Yeah.
This can be equated to mCp dt. What is m? M is mass flow rate. Mass flow rate
Yeah.
is rho AV.
Mm-hmm.
Rho AV, density, area, velocity, m dot.
Mm-hmm.
Cp of air 1007, and dt would be final temperature minus 10.
Yeah.
T minus final 10, right?
Yeah.
Because it would enter at 10 degrees Celsius and come out at T final degree Celsius.
Yeah.
Right? So this 5040 will be substituted over here. We have the density as 1.187. This is the value. 1.184. Area of cross section. Over here it will be area of cross section.
Mm-hmm.
This m dot will always have cross section. Cross section of rectangle is 0.15 into 0.2. You know the cross section area of rectangle, right?
Yeah, just the area of the rectangle, right?
Yeah, simple area of rectangle. It's
Okay.
late over there, I can understand. Okay.
Yeah.
Velocity. Velocity is 4.5.
Mm-hmm.
Okay. Let's try to simplify and find the TF, final temperature of the air. It is 5040 divided by 1.184 into 0.15 into 0.2 into 45 into 1007 plus 10. How much did you get?
Working on it, Peter.
$41.3123.
Yeah.
Okay. This is the final temperature of air coming outside.
Yeah.
Okay. This is the exit temperature, wall air exit temperature. Right? But we want the wall exit temperature.
Yeah.
If you understand, if we draw the graph, the
Mhm.
air is getting heated. Air is getting heated as in, you can say, the line would go like this. The 10 degrees Celsius air is exiting at 41.3123 degrees Celsius, right?
Yeah.
And the other fluid will get, or the wall will get cooled.
Mm-hmm.
It is possible only in counterflow, by the way, to have uniform heat flux.
Okay.
Uniform heat flux is possible only in counterflow. So the temperature would be, this temperature is something they are asking you. Outlet temperature. This is inlet temperature, right?
Mm-hmm. Yeah.
Okay. Now we need to find this temperature. This is something which is unknown. How to find it? What would you use? How would you solve it?
So this is between surface and surface, right?
Okay, I'll explain. Don't worry. Uniform heat flux is only possible when this temperature difference is equal to this temperature difference.
Yes.
So if you remember, I told you whenever the temperature difference is same, delta T mean
It's T1 or
to
T2.
delta T1 equal to delta T2.
Yeah.
Okay, in that case, you can simply take the difference between these two.
Yeah.
Like you can say, I want TO and it will be TO minus 10 degrees Celsius.
Yeah.
Right? So this is delta T mean itself now. Since this is delta T mean itself, we can use the formula of Q is equal to H A delta T mean.
Yeah.
When H is given or what? Or we need to calculate.
So which we have to calculate?
We need to calculate H also.
Yeah.
Okay, fine. So Q is there. We have the value of Q.
Mm-hmm.
A would be surface area. Surface area is basically this value. Okay, 2
Yeah.
into 0.15 plus 0.2 into L.
Yeah.
And delta T mean would be T naught minus 10 degrees Celsius.
Mm-hmm.
Okay. H, how to find H now?
We have to find whether the flow is turbulent with the Reynolds number and all.
Yep. So now, first of all, we need to find RE.
Yeah.
RE will be equal to rho V D by mu.
Yeah.
What are the values do we have? We have rho, we have nu. So we will be using the formula VD by nu. VD by nu. Okay. In this case, the duct is rectangular, so we need to also find the diameter, hydraulic diameter.
Mm-hmm.
How to find the hydraulic diameter? Do you remember?
4 AC over perimeter.
Perfect. 4A by P. 4A by P. 4A. A would be cross section itself. 0.15 into 0.2.
Yeah.
0.15 into 0.2. And perimeter would be twice 0.15 plus 0.12. So 0.2.
0.2.
Yeah. So what would be the diameter? 4 into
0.1714.
0.15 plus 0.2. How much did you get?
0.1714.
Zero 0.17143. Okay. 0.17143.
Yeah.
So this was diameter. We can find RE. RE would be velocity is 4.5. Diameter is 0.17143 and nu is 1.562 into 10 raised to minus 5, right?
Yeah.
How much is the value? 4.5 into 0.17143 divided by 1.562 into 10 raised to minus 5. Okay, I got a big number.
49,387.
49,000, right? It is 49387.6, which is more than 4,000.
Yeah. Can I just check something with you?
Yeah, sure.
Why did you change it to VD over V?
It's VD by nu.
Oh, okay.
Nu. See, this is nu. See, very easy. RE is equal to rho VD by mu. It's
Yeah.
also VD by nu because nu is equal to mu by rho.
Oh, okay.
Kinematic viscosity, dynamic viscosity upon density.
Okay.
Okay, RE is done. So we can use the Nusselt number equation for turbulent flow.
Yeah.
Nusselt number equation for turbulent flow, you got the
Yeah, I got the formula. 0.023.
Yeah, formula 0.023 RE raised to 0.8
8.
and PR raised to,
0.4.
are you sure?
Heating, right?
0.4 or 0.3?
0.4 for heating.
Okay.
Correct?
0.4 for heating. Ah, yeah, air is getting heated. Sorry. 0.4. Air is getting heated from 10 to 41. So it will be 0.4. So
Okay.
now we can find Nusselt number. Nusselt number. They have given us Prandtl number or not? They have
Sorry?
0.7295, right? Prandtl number.
Yeah.
Yeah.
0.7296, I think, something like that.
0.023 into RE is
49387.
okay, and PR is
0.7296.
0.4. How much did you get?
115.305.
115.307. I've got it. No problem. Okay. And this is equal to HD by K.
Yeah.
Okay. So we can find the value of H, which will be is equal to answer into K is 0.0255
551.
upon diameter was 0.1714. 17.15.
Yeah, I go 16.
Oh yeah, 17.158. It is equal.
Okay.
H is obtained. We will substitute over here.
Mhm.
Question is done.
Okay.
Okay, see, what I think you might be facing or you might be having trouble with is the formula that they have used to find the value.
Mhm.
Did you understand exact solution? How would you solve it?
Yeah, I did, I think.
See, I think you should always remember this graph which I have taught.
Yeah.
Because whenever there will be heat flux constant, whenever there will be a constant heat flux, there will be only two kind of diagram. Either it will go upward, one fluid will go upward.
Mhm.
I will just, do you need to take a note of this? You can simply use the recording, okay?
Yeah, no problem.
See, I will explain you about Q type of question, like whenever the Q would be constant, what type of graph would be asked,
Okay.
or what type of graph you must draw. So in this case, the air was getting heated, cold air was getting heated. So something, if it is if some fluid is getting heated, it would go like this.
Mhm.
It will be like dt initial, and this would be T final.
Yeah.
And the Q constant is maintained only when the gap between both the graph is constant throughout,
Mhm.
like both the slopes. If I would draw the another temperature line, it is very important that this gap is always constant, always same throughout.
Yeah.
So if something is going up, if something is getting heated, other thing might get cooled.
Okay.
Okay. Now Ti is getting heated. Now it was getting heated, and the pipe was getting cooled. This
Mhm.
would be pipe's inlet temperature. So let us say it is TE and this is TO.
Okay.
And they wanted us to find this value, right?
Yeah.
Now you need to focus on the required unknown. Because they were asking you this value, we used delta T1. Had they been asking us this value, you would use delta T2.
Yeah.
You should know that delta T mean will be equal to delta T1 is equal to delta T2. Okay, what is the second type of graph possible, or what another combination would be? In this case, this was getting heated.
Mhm.
It can be a case where fluid was getting cooled. How would the fluid get cooled? It will get cooled in this manner,
Yeah.
right? So
Yeah.
this would be Ti, this would be Tf, and another fluid would be like this. The gap will always remain constant. The gap will always remain constant. Like the gap means the temperature difference, this temperature difference, right?
Okay.
It's like
Yeah.
two lines moving parallel. This is T entry and this is T outlet. This will be delta T1 and this will be delta T2. Delta T mean will be equal to delta T1 equal to delta T2. What is delta T1? Delta T1 is temperature difference between T2. Delta T2 is temperature difference between these two. See, these are the only two graphs you will be having if the question comes with Q constant.
Okay.
There is no other possibility. Okay.
Okay.
So this is something I think it might be confusing. Otherwise, the question is very straightforward and very easy. If you have any doubt, just ask me.
Okay.
So last question, sixth question.
Yeah, we can stop after this.
Okay. Air at 110 degrees is entered in 18 centimeter diameter, 9 meter long duct. The duct is observed to be nearly isothermal. Okay. The question is almost same like question number 4. Okay.
Yeah. I got it all the way up to.
You tell me the procedure. I will check if you are right or not. Okay. Tell me the procedure.
Okay, first I found the Reynolds number.
Okay.
I found out it's turbulent flow.
Okay. I'll just write down. Okay.
And then
You found RE and you
Yeah.
found that it is more than 4,000. Okay. Next.
Yeah. Then I found the Nusselt number.
Yes, correct. By using the 0.023 line equation.
Correct. Yeah.
Okay.
And then it's for cooling. So I use 0.3.
Oh, perfect. N equal to 0.3.
Yeah.
So
And
cooling
then,
yes, cooling. Correct.
yeah. And then I use the formula to find H.
H was calculated by using HADYK. Okay.
Yeah, I got 11.1763.
Okay.
And then after that, I tried to use the Q equals to HAS delta T
Perfect.
log. But that's where I got a bit confused.
Okay. Fine. Again, this question is about isothermal question. Right?
Yeah.
The graph we could draw is the air is getting cooled. Since the
Yeah.
air is getting cooled, it means its graph would go like this.
Correct.
And the one which is helping it cool would be at lesser temperature. It will be drawn downward.
And constant. Yeah.
Yeah, it is 110 at the entry and it is not given at the outlet, right?
No.
And this one is maintained at 85 over here also and 85 over here also.
Yes.
Okay. First of all, we need to find this temperature. Okay. To find that temperature, we have to use formula MCP dt. Q equal to MCP dt. Okay.
Yeah.
MCP dt will be equated to HA delta TSM. TM.
Yeah.
This question is painful. You know what?
Just a lot of steps, right?
Painful because there's a lot of mathematical.
Yeah. I think that's why I gave up too.
Because the temperature parts comes in between the log.
Yeah.
It ruins everything. You'll have to take anti-log and then solve it anyhow.
Yeah.
Okay. Let us give it a try.
Okay.
Let's see if we can do it. Okay.
Yeah.
We will. There is another method also called as NTU method. Okay. I don't know if you're ready to learn it. If you are, I can teach. But
Okay.
if you want to solve it by your teacher's method, even I'll explain that. Okay.
Okay.
Let's go ahead. Q is equal to HAS delta T mean equal to MCP dt. See the tricky part you have done now. Like calculating H used to be always tricky. So you calculated that.
Yeah.
H is known, AS is known. Something which will trouble you is now the temperatures.
Yeah.
Because in this case, the one temperature which is unknown, it will be in between the log. Okay. So how to do it? Let's see. H is. Do you remember one of the formula was simplified and given in the sheet of formula?
Wait, let me just see here.
I think I remember they had simplified it. No. They haven't simplified. They simply gave you the formula.
The constant surface temperature, right? Oh, I think they did.
Yeah, right. So this
Yeah, I'll send it to you now,
the constant surface temperature T
right?
equal to Ts minus. Remember?
Is it this one? The second one?
Yeah, the TE formula. Yes, exactly. If you
Okay.
can use or if you can remember that formula, things will.
Okay.
I think that is something you have to do now. The TEs need to be calculated, right?
Yeah.
Equal to Ts minus exponential is it means e raised to. It is minus HAS upon m dot Cp.
Mhm.
Can you remember this, or we need, or do you want me to simplify this to do it the longer way?
No, this is okay because it's in the formula sheet also. I can just use it.
Okay, if you can remember this, it is fine. But if you want, you can do one thing also. Like what? See, I'll just explain. Okay, if at all you can do it, just do it. Like HAS and MCP can be taken on the other side.
Okay.
Right? The formula would look like HAS upon MCP.
Yeah.
Delta T mean is equal to dt.
Uh-huh.
Delta T mean? Delta T mean is equal to delta T2 minus delta T1 upon ln delta T2 by delta T1.
Yeah.
Now what is delta T2? Delta T2 would be, what are the temperatures?
The temperatures given
110 and 85, no?
yeah, 110 and 85.
Okay, you can take this as 110 minus 85, and delta T1 can be taken as T outlet or T exit minus 85, right?
Okay. Mhm.
Let us say it is TE that we need to calculate. Exit is okay, or you want to use some other term?
Exit is okay.
Okay.
Yeah.
So let us substitute over here. This will look like 110 minus 85 minus TE minus 85 whole upon ln 110 minus 85 upon TE minus 85. Okay, this can be simplified. The numerator minus 85 and plus 85 will get cancelled out.
Yeah.
This will look like 110 minus TE upon ln. You can simplify it or you can keep it as it is. 110 minus 85 upon TE minus 85. This is the T mean, okay? Delta T mean.
Yeah.
You can substitute it over here. So this will be like HA upon MCP into 110 minus TE upon ln 110 minus 85 upon TE minus 85, and dt would be right.
Yeah. Yeah.
The final temperature and the exit temperature, the inlet temperature and the exit temperature.
Yeah.
Okay. So this can get cancelled out.
Oh yeah.
So this can be taken over here. So this will look like HA upon MCP will be equal to ln 110 minus 85
over TE.
TE minus 85.
Yeah.
Okay. Now we can take antilog.
Yeah.
Antilog is basically exponential.
Exponential.
It will look like 110 minus 85 upon TE minus 85 is equal to e raised to HA upon MCP, right?
Yeah.
So now we can do it. One thing is that we can take this on the left side and take this in the denominator. So this will look like 110 minus 85 upon exponential raised to x, let us say, TE minus 85. I think now it is easy to calculate TE.
Yeah.
TE would be 110 minus 85 upon exponential something plus 85. And see, that is exactly what they have given. Kind of, see, 85 surface temperature, 85 is the surface temperature.
Correct.
See, here they have negative sign over here, but at the same time they have negative sign over here. You should know that exponential negative sign can be taken out and it will become positive. So that's how this formula looks exactly same like.
Okay.
Or maybe other way I would say. You see, it is TS minus TI. TS is 85 and TI is 100.
100.
Our it is 110 minus 85.
But there's no
It
negative.
is negative sign.
Yeah.
Okay, one more thing. If it is taken in the numerator, it will get negative.
Yeah.
So see, this is the same formula which we have mathematically simplified. If at all you forget the formula in exam, just go through this. This is a longer step, but I think I would prefer this.
Okay.
Okay. Anything else?
No.
You have sent me that graph of the question. Could you solve it?
That is under natural convection and radiation, right?
Yeah.
Yeah, I have not got to that yet.
Okay, fine.
Maybe I will look through the videos and all, then we can do this the next lesson for the radiation.
When do you have your exam?
Saturday.
When?
Saturday on the 13th.
Saturday. Okay. So maybe let's have the next session by day after tomorrow itself, or tomorrow, day after tomorrow, whatever it is.
Tomorrow is good actually. Is that okay for you?
Tomorrow I will have to update because I have a meeting in the morning. If it gets cancelled out, then we can have a lecture.
We can do it at night.
Yeah, night is okay. Night is anytime okay.
Time is good.
Night is okay. We can have a session in the night tomorrow.
Okay, great. Then we'll do it tomorrow.
Okay, sure.
Yeah, so then I'll prepare the natural convection and radiation for tomorrow.
Okay.
And we can go through that.
Sure.
Okay.
Okay.
So all these values I have, right, for this formula, like the H we found.
Yeah.
Mass flow rate also we can find.
Yeah.
And CP is given, right? Yeah, okay. So this is the final answer, right? The exit temperature?
Yeah, that is the answer they wanted.
Okay.
These questions look smaller, but they are really big, okay? Like
Wow.
the way they have asked, it's like it's a multiple choice question, but you need to really give your everything to solve it.
Yeah. I have some I need to go through these. Like I think you went through it with me, but just in case I have some questions, can I maybe
Yeah, sure.
check with you? I haven't prepared it yet, but like I need to go through these. Just send it over now. Like I need to know this. And then
What is mean temperature? What is thermal entry? What?
yeah, I think you went through all this, right? The other
We
time.
can discuss it, no issues.
Yeah. So I'll look through them, the previous lectures and everything, and try to answer as much as I can. And then can we go through, because I want the proper way of writing it for the answers.
No problem, no problem.
Just in case I miss something out, or the definition is wrong or something.
Okay, no
So
problem.
let me go through it, and then we can do this tomorrow as well with the 2 questions.
Okay, if possible, just write down the answers if you have.
Yeah, I will write down whatever I feel the answer is.
Yeah, that is fine.
We go through them.
Yeah, no problem, no problem.
Okay, then. All right, yeah. So I'll do this tomorrow then.
Okay,
Okay, then we have the lesson around this time. Is it okay for you?
this time is okay.
Like about maybe 8:30 your time?
Yep, fine.
Sounds good. Okay.
Okay.
All right. Thank you. So
good
I will need a favor. I need you to send me this recording like by today, so I can review
I can do
it.
it. No problem. I can do it.
Okay, yeah. Thank you so much.
Okay. Good night.
Good night. Thank you. Bye.